Voy a ir aceptando a los que vayan a empezar, por favor.
Good afternoon to everyone.
Hello, good afternoon. How are you doing?
How was the sound yesterday on your side?
Uh, I couldn't be at the at the ending, but I don't know. I didn't heard any complaints, so I think it's okay. It was okay.
Anyway, we don't have choice.
Yeah. Also, we don't have, but I can hear you clearly. So I think the rest is the same. So the first module is by Dr. Tatiana Melnikova, right?
No, the first is mine.
Ah, the first is yours. Ah,
Uh-huh.
sorry.
Radio ecology. Right. The whole week except for Thursday. I will be the first.
All
On
right.
Thursday, Professor Melnikova will be the first. And Professor Fomin will be always the last. He doesn't sleep in nights, so he agreed
Ah,
to be the last.
okay. What time is there?
Now it is 7 in the evening,
Ah,
so we finish like quarter to midnight.
oh wow, midnight.
Yes.
Oh wow, it's almost 12. It's just 12 hours. Okay. So someone was saying hi. Okay, but this is not your first time doing this, right? I think you have another cycle of conferences last year.
Yes, the last was in January, I think. Yeah, in
January
January that year. That year,
of
more
this
than a
year.
year ago.
Oh,
That year in 2022,
okay.
if I'm not mistaken. Yeah.
Oh,
Well, I'm lucky. I several times visited your country,
oh really?
Budapest and other places also. Yeah, before coronavirus.
Yeah, yeah. Maybe some of our colleagues and perhaps some students also went there, right, to the MEPhI University.
Actually, we have more and more experience of this type. There are already some Bolivian graduates from our university. I
Oh,
see that yesterday somebody was, but well, that person was from Moscow headquarters. I think so.
ah, okay.
Yeah, we have two main campuses in Moscow and in Obninsk for foreign students.
Oh, oh,
Hmm. And about 15 branches for,
oh,
well,
wow.
around the country. Yes, and even in some other countries, two campuses in abroad.
Oh, wow. It's a huge university.
Actually, we are not as huge because our university is specialized on nuclear field, so we are not as large actually.
Ah, okay. But that's impressive.
I think that even UMSA is larger in number of students.
And number of the students. Maybe um, here I know I don't know if the number is correct this year, but the past years, we were around 80,000 students, maybe around that. It's not that large, consider our population, no? But it's the larger here in La Paz, in the department of La Paz, yes.
Yes.
Mm. But our physics department is small compared with that number. And yeah, and also here inside the physics department, we have a group of cosmic ray physics and also related with particle physics, and is where I work right now.
Okay, yeah. Of course, you know much more than was given yesterday in my lecture. Only
Yeah.
short.
No, but it was a very interesting introduction, I think, for the uh,
Yeah,
general
of
people.
course, there are different people. Yes.
Yeah, yeah. So we have here a larger trajectory about cosmic rays. One of the foundation of our faculty was that for that reason, because here was established a cosmic ray laboratory at Chacaltaya. If you were here, maybe you heard about that, the
Yes,
laboratory.
I've heard. Didn't visit it,
Uh,
unfortunately, but I've heard. Yes.
Maybe next time we can arrange a visit for there because very interesting.
Dream of next visit.
Yeah, of course. Uh, so I think it's already noon here, and maybe we can start. I don't know if.
Well, we can start here. Give other students to join us.
Okay, let me.
Yesterday was a huge amount of participants. It's very nice. Thank you for the interest, and it is because of organizers, I believe.
Yeah. I think there were about 80 participants,
Oh, even around 100.
around 100. Wow, more than so.
Yes, some moments, yes.
Okay, so let me
Well, okay. Yeah, let me start then.
let me ask to the local committee if you are ready to start. They they need to record the presentation, and I make sure if they are ready. Okay. Eh, Kevin o alguien del Club de Física están listos ya para grabar.
Ya se está grabando, creo que desde las 12 menos 10. Luego lo va a prestar.
Ok,
Luego se va a hacer.
ok, Kevin. Entonces, ¿puedo dar inicio?
Dale, vamos, a ver.
Ok. Mm. Okay, good afternoon and welcome to the second day of these lectures. We are going to start with the module 3, module 1, sorry. And according with our schedule is module 3, is radiation ecology by Professor Oudalova. So when you are ready, Professor, we are ready.
Okay, then I will start. So, good afternoon, dear students, dear participants. Let's continue our lectures. So, I'll remind you that yesterday I considered natural radioactivity. We discussed these things about natural sources of radioactivity, both normal sources and situations where natural radioactivity is increased because of natural reasons or because of human activities. Other lessons planned in this module are devoted to artificial radioactivity. All other lessons will be about artificial radionuclides. We really need to know about natural radioactivity because you saw that in some situations we have really high levels and we must be prepared for it, yeah, and know how to react, what to do in these cases. But still, we are not so much concerned about natural radioactivity as about artificial, because artificial is in natural, yeah. It mustn't be in the environment, and always man-made radionuclides, artificial radionuclides are considered as contamination. So I'm going to talk about some theoretical regularities of behavior of technogenic radionuclides on the example of terrestrial environments. In general, radioecology is a quite large science, and of course we can't cover everything. We will concentrate on the main important and maybe best illustrating fields for the radioecology, like terrestrial environments. And here we will discuss behavior of radionuclides on typical food chain, soil, plant, animals, and human food. So this is kind of theory. And last two lessons will look a bit more practical. I mean that I'm going to discuss some experience which we have now in this field, yeah, how to deal with radioactively contaminated territories. And in the last lesson, I hope that you will be active enough to participate in practical exercises, calculations of some problems. So let's start with this topic of technogenic radionuclides in terrestrial environments. And when we think about this type of environments, we consider, as I mentioned already, food chain, and we shall consider how radionuclides can travel through this chain, starting from the beginning, and then step by step go into soil, then into plant and animal and so on. So let's start from the discussion of sources of artificial radioactivity in the environment. Well, again, let's remember that there are natural sources. And by the way, when we talk about contamination of the environment, we mean really radioactive material, not rays or beams of charged particles, but radionuclides. So among natural radionuclides, we yesterday discussed the presence of cosmogenic radionuclides, also ancient primordial radionuclides. Some of them are like single radionuclides, don't given families. Others have families and produce daughter products. So these are our natural radionuclides. What are artificial radionuclides? What are the sources of artificial radionuclides? Okay, there is some noise in our room. So you can think yourself, and maybe you have some ideas about sources of artificial radionuclides, but to not waste our time, I will open my closed part. And not always, or I would even say that only in few cases I obtain correct answers from my audience. What are sources of artificial radionuclides in the environment? And you see, the first reason, the most important reason, the most important source is global nuclear testing, global contamination from testing of nuclear weapons, which happened in the last century, mostly in the middle of last century. It is not much discussed today. Well, we will see why actually. Then very often people remember about radiation accidents. Yes, of course, we have some important radiation accidents like Chernobyl or Fukushima accidents. And of course, they are sources of artificial contamination, of technogenic contamination of the environment. And then we can, in principle, find some other additional potential sources. And well, let me discuss a bit this last panel now, because I'm not going to pay much attention to this except for medicine. So radioactive wastes and spent nuclear fuel. Of course, these are sources, yes, potential sources, but in case we manage them correctly, they don't produce any danger, any contamination for the environment. In the past, when we didn't know what to do with them correctly, yeah, and sometimes radioactive wastes were spilled into the open rivers, or some solid wastes were um, hidden in soils and so on. It was, of course, wrong practices. Now activity is organized very well, and there are well-organized systems of management of these things, both of radioactive waste and spent nuclear fuel. I will talk a bit later about medicine. This thing, yeah. So you now know a bit more about this because you started your program in your country with exploitation of radiation technologies. Yeah, you have already radiation center, and also, well, I'm not sure what the situation now with medical center, but seems it's also active, some activities there, right? And when we have such activities, we can expect also some potential contamination, both in the case of administered releases or in case of some unexpected releases into the environment. But here I can be absolutely sure in telling you that these sources don't have much importance in global sense. Probably in case of some local accidents, it could be not very good for workers involved in such accidents or for some very local environments. But these industries, uh, industrial applications, agriculture, scientific applications, and many others, don't give us many problems. About nuclear power engineering also I'll tell a bit later, but I myself believe that nuclear power plants are the last in the list of potential sources of radioactive contamination of the environment. So, global nuclear testing and global contamination of these nuclear tests. Probably you've heard something about it, yeah. There were a large amount of these tests. On next slide, I have some statistics, some general statistics of them. And from this picture, very impressive, yeah, you can understand very well that contamination of the environment after such events could be really huge. We consider different types of such explosions, different types of tests, and from the viewpoint of radioecology, it is very important if they are atmospheric or above ground tests, or underground or underwater tests, because this is initial point of dispersion of contamination, and then we can understand what is the future for these clouds or some contaminated waters and so on. So the worst case are atmospheric explosions, and the especially bad situation when these atmospheric explosions are high. Because in case if radioactive substances appear in stratosphere, they start participating in global atmospheric transfer on our Earth. And unfortunately, there were such explosions. Because of them, transfer of radionuclides appeared really globally. And for example, your country never participated in this, yeah? And nobody carried and conducted nuclear tests on your territory. But unfortunately, be absolutely sure, on your territory there are depositions, fallouts of these radionuclides born in these nuclear tests. This is global situation, absolutely everywhere we have rests of them. So this is some statistic and amount of tests conducted by different countries, and also some history in years, how it was. So on the diagram, you see the number of nuclear tests conducted in different years. And in black color, tests in open environments are shown, so the atmospheric or above ground tests in the higher layers of atmosphere. And as I try to explain, this is the worst situation from the viewpoint of contamination of the environment. After 1963, the decision was taken to limit these tests and stop any tests in these open environments, or actually in 3 medias. After 1963, only underground tests were legal, and many of them, you see this underground part, yes, many of them were conducted till 1996, when the full ban was taken. The decision was taken about the full ban of these tests. And after it, still we have some sad accidents with unauthorized tests done by some countries, but only few of them. Right. What are the consequences in terms of contamination? By the way, I shall maybe mention that these first activities, they were done this way because at these first steps, nobody cared about contamination of the environment. Just it was not clear that it can happen. And scales and consequences of this were really unknown and not unexpected, but just nobody thought about it. Later in the course of these tests, which started in 1945, they started, and during these years it became clear what we have as a consequence of them in terms of people exposure, large transfer of radionuclides, and so on. This is why this first ban was taken. Right, so the consequences. This is a large topic, actually, if you start discussing in details. But in very simple words, we can refer just to doses, to global population. Of course, they are kind of average doses. So you see this diagram here. It shows these doses in different years, averaged. Of course, in test sites close to epicenters of these tests, and also along the traces of depositions of fallouts, doses could be larger. In general, they try to conduct these tests in empty territories without population living there. Also, there was some unexpected things, nevertheless, and overexposure of some groups of people. But still, let's look at the values of doses. You see the largest doses were around 1963, and this peak was 0.11 millisievert in this year. If you remember yesterday lecture, and compare it to natural background, 2.4 millisievert per year from natural background on average, you see that even in the worst situation, doses delivered were low. On average, I repeat that this is the average estimations. Well, after the nuclear bomb explosion, we deal with a large amount of radionuclides. It could be up to 200 radioisotopes, and many of them are short-lived or have some average half-lives. So with time, the exposure level decreases very fast. But some radioisotopes have quite long half-lives, and it means that they will stay in our environment for a very long period of time, for centuries, or maybe even for thousands of years. This is why, first of all, there is fast decline in doses with time, yes, but on the other hand, still now and in future, we will have some additional exposure from these events. So this is estimation for nowadays. And here you can see the most important radionuclides, which still play a role in forming exposure doses to human population now and in the future. Well, interesting to see which isotopes are they. So these first two isotopes are very famous in all fields around nuclear. So from radioecology point of view, they are very bad isotopes, I would say, both because of their nuclear properties and because of the chemical properties of these chemical elements, because they are very mobile in the environment and can travel through this food chain in the environment. And they have essential half-lives about 30 years. It means that during first two half-lives, 60 years, yes, they deposit most part of the energy through the doses absorbed by living organisms, by us human. During one human life, essential doses could be formed from these two isotopes. Also, we always pay attention to these two isotopes. Yes, by the way, again about cesium-137 and strontium-90. If you studied nuclear physics, you maybe know dependence of probability, in fusion reaction, different isotopes could be formed, and there is such a dependence on atomic number and the probability of different types of isotopes. So these two peaks are around 130. Sorry, this is about 90, and this is about 130. So it means that really strontium-90 is here in this peak, and cesium-137 is here as really important isotopes appearing with high probability in these reactions. So the amount is essential. Two other isotopes, carbon-14 and tritium, are important because of their biological properties, because of need for them in biological life. Yeah, so they are included in cells and so on, in living tissues, and also can deliver essential doses to us. So today it is important to measure, to control global levels of at least these four isotopes after nuclear weapons tests. The next important cause of the environment contamination with radionuclides are radiation accidents, as it was mentioned. Yeah, I will not discuss in details. I just would like to mention that, of course, there are not only Chernobyl and Fukushima accidents, and there are much more of them, but they have different severity. After the Chernobyl accident, international organizations decided to establish this scale, international nuclear event scale, which is used to range different incidents and accidents involving radioactive materials or radioactive sources. And now they, range all events which happen according to this scale. There are 7 levels, as you see. The highest, the 7th level, is given to major accidents, which large contamination of territories and also a large population of people involved in consequences. And the other levels are lower, yeah, and difference in consequences is approximately 10 times between these levels. So this is kind of logarithmic scale. And in general, well, I don't have on hand exact information, but I must say that in total, number of accidents is counted not in dozens or hundreds, but in thousands. Of course, most of them are here, yeah, on the bottom. So level 7, major accidents. Level 7 was given to these two accidents, Chernobyl and Fukushima accident. And level 6 up to now is given only to one accident, which happened in Soviet Union in our Urals in 1957, and is called the Kyshtym accident. So these three are most serious, most important, and involved really contamination of essential territories. But comparing to global fallouts after nuclear tests, they are not as essential. Still, this is only regional contamination, not global. Well, then about nuclear power engineering. Yeah, today this is one of the most important industries involving nuclear technologies and applying nuclear technologies. And we know that many countries around the world own nuclear power plants, construct new or are going to construct them in future. Despite some period of negative attitude to nuclear power engineering after the accidents, actually, today there is increasing positive attitude to this type of electricity production. Well, and many countries are interested in it. At the normal operation of any nuclear power plant, there are some releases and discharges of radioactive substances. Don't be scared by it. This is normal activities. They are administered, and they are considered and limited to absolutely safe level. And well, the same happens in all industrial enterprises. Always at any technological process, we produce some contamination of the environment, chemical or thermal or any other types of contamination or pollution. So these administered releases create extremely low additional doses of radiation. So you see this estimation here. And if we compare it to this or to this value, yeah, you see what is it. Of course, this is negligible. It is nearly zero. Remember in yesterday lecture, I stressed attention on the radioactive contamination around thermal power plants because of combustion of fossil fuels. Believe me, it is much more serious, especially if there are no modern protective equipment on these thermal power plants. Okay, and additionally to these main groups of artificial contaminants, artificial sources, you see natural and artificial, yes, which are present in the environment. Human beings are exposed to additional source, which is a result of medical applications. So understand the difference. Yeah, this group of sources are present in the environment, and we are exposed because they are there. But medical exposures are very different. We decide to apply these medical exposures for different purposes, mainly for diagnostical purposes, and also for some therapeutic purposes. Also, therapeutic applications are low. So yeah, this is exposure of patients. There is no contamination of the environment during these procedures. Most of them use sealed sources of radioactivity, and in this case, the radioactive contamination is impossible in principle, and only in radionuclide medicine some very low amounts can appear in the environment, but all these processes are controlled. So actually, for the environment, there is no negative consequences. But for patients, of course, we deliver additional doses. Maybe you will be surprised to see how large is contribution from radiation and nuclear medicine today to the doses of people exposure. So see, this is a bit old data actually. You see, this is from 2008. And in blue colors, natural sources are given. And this one is medical exposure. I believe that in this nearly 20 years after 2080, this contribution increased much to 40% on average in the world. And in developed countries, medical exposures are very large. Well, for example, computer tomography is used very intensively in developed countries. And from one hand, we believe that this is very good technique, yeah, CT and also other diagnostical methods. Yes, they are very good, but they increase doses of exposure. And in USA and in other developed countries, partially in Russia too, and well, in other European countries, average doses from medical exposure now much more than 1 millisievert per year. So I don't want to say that this is very bad. I just like to emphasize that we have different sources of exposure and we must understand how serious are they and do we need controlling them or limiting them. Well, so let's look again at this diagram. And first conclusion is doses from natural sources are prevalent. Conclusion two, medical exposure is very important. Where are our artificial sources, our nuclear tests, radiation accidents, where are they? Actually, they are here. This thin pi, yeah, 0.01 millisievert per year on average are brought by these so-called other sources, which include fallouts after nuclear tests, the most important accidents, and, well, other possible artificial sources. I'd like all our students in our university and everywhere got it very well and understand. And you know, there are a lot of words in internet and mass media everywhere about very bad consequences of nuclear power engineering or other nuclear technologies applications. Many of them are lies. And these people who talk about them, they just, they're not professional, they don't know these things. Still, I must emphasize that these data are average. Of course, there are sites, there are local territories where we have radiological problems because of artificial contamination. And this is why we study them in such sciences as radioecology. Okay, so next piece of this lecture is a talk about process of appearance of radionuclides in soils. So these main sources from my previous talk, well, let's see here, for example, nuclear tests, radiation accidents, and even administered releases from nuclear installations. Most of them appear into atmosphere. Only small amounts from our past experience go into water bodies, into global hydrosphere. By the way, the Fukushima accident is one of such impressive examples. There was release into atmosphere too, but a lot of radioactive materials were discharged into the ocean. Still, in most cases, first we have releases into atmosphere. This is why in radioecology we talk a lot about this atmospheric path over soils contamination or terrestrial environments contamination. So what can we have in principle in our environment as artificial radiant lights? There could be different ways of classification of these radiant lights. This is one of these types. We can have fission products. Both in all these sources, like nuclear bombs explosions or nuclear reactors accidents and so on, we deal with fission reaction. And remember, about 200 radioisotopes can appear after it in the environment. Here are shown some of them which are especially important. And you see in blue color already mentioned strontium-90 and cesium-137, which are of special concern for consequences from such events. Then a second group which can be present in the environment are so-called radiant lights of induced radioactivity. How do they appear? In case we have very powerful radiations, in first turn neutron radiations, and also some very powerful gamma rays can be able to start nuclear reaction of activation. It means that stable atoms, stable nucleus, can interact with these fluxes of neutrons, for example. Nuclear reactions start there, and as a result, we will have unstable product of this reaction. They are these radiant lights of induced radioactivity. Many of them belong to metals, just because many all installations are constructed of metals or different alloys, different mixtures of metals, and while these reactions are more probable, leading to formation of these isotopes. Usually they are not very serious in terms of consequences because they could be or short-lived or inert in the environment, so they don't go further, don't disperse in the environment. And here you see also mentioned already tritium and radiocarbon, which could be induced in atmosphere after neutrons interaction with atoms of atmosphere. If you again remember yesterday lecture about cosmogenic radiant lights, process is the same, but origins are different. Natural cosmogenic radiant lights are tritium and radiocarbon, and the same isotopes, but formed because of artificial processes. And the last group, transuranic elements, which also could be products of these nuclear reactions in case of nuclear explosions or processes inside of nuclear installations. In the long run, after accidents, not all of these radionuclides are important. As you can guess, only those which are emphasized by color, by this bright blue color, yeah, are especially important, and we mostly concentrate on consideration of these radionuclides. Then, very important is what is the state of radionuclides and releases. To some extent, I talk about aggregate state, but not completely. In radioecology, we consider the following types of states of radionuclides. First are gases or gaseous compounds. Among them, we can have inert radioactive gases, which are produced in very large quantities in fission reactions. And also other types of compounds or elements like iodine and iodine compounds, organic and molecular iodine also, and some other compounds which could be very volatile and considered like gaseous. Then the second group are called aerosols. They are formed um, at evaporation of um, hot solid fuel in the epicenter of such explosion or from active zone of reactor. They are primary aerosols if they are formed at an evaporation. And also there could be secondary aerosols which are formed in atmosphere already when our imagine explosion, yeah, and from epicenter when all this fuel is concentrated, we have thermal and nuclear explosion and have these products in the atmosphere where they experience very fast decrease of temperature and a change of pressure. So in this condition, they are easily concentrated, condensed on any carriers which can appear in atmosphere, like dust particles or water drops or even pollen of plants. So these are secondary aerosols or condensation type aerosols. And both primary and secondary aerosols, they look like very small particles, but radioactive particles. Right. And the third state of radionuclides, which we always consider, are hot particles. In principle, they are just very small um, pieces of nuclear fuel. They could be thrown out of the epicenter just by mechanical force of explosion. Um, well, so volatile compounds will go in form of gases, yeah. Also, chemical elements which have low temperatures of melting will go in form of aerosols. Inside of fuel particles, fuel solids, we will have such chemical elements which are very refractory and also chemically inert. Usually content of fuel solids more or less understandable, and usually very inert chemicals are contained inside of them. Also, they are usually large compared to aerosols. Large means heavy. As a consequence, they will fall down on the surface, not very far from the epicenter of our event. While aerosols are light and could be dispersed to very large distances, depending on the size and mass of these aerosol particles. So for soil contamination, of course, these two groups of our releases are important because they can fall down on the surface. So at first, if we have atmospheric releases, right, all these types of radioactive materials appear in atmosphere. They could be considered as a radioactive cloud, and it will mm, move in atmosphere in dependence on climatic conditions, temperature, wind direction, and so on. And with time, they will be deposited on the surface. Well, this table I usually use as an example to illustrate how different properties of elements appeared among these radioisotopes influence on their future fate and on their importance for doses, for health consequences, and so on. This table is based on the Chernobyl accident again. Well, just because this is large accident and a lot of information is collected about it and studied in details. Here in this table, only some radioisotopes are shown, but most important for this situation. We see in first column, we have the list of isotopes. In second column, amounts of activity which were present inside of a reactor at the moment of accident is presented. Understand that these values, they are not measured, but they are just calculated from known regularities, from known models of these fuel companies. And if we look at this column, we will see that the largest amounts at this moment are here, yeah. So they are volatile compounds and gaseous compounds, and also strontium 89 in large amounts, and these elements are also remarkable amounts are presented here. Then next column, release. Yeah, percentage of initial radioactivity from the reactor which was released in the atmosphere. You see the idea here, yeah, gaseous compounds are released completely, and then the more refractory are these chemical elements, the less is the amount of released material into open environment. And here, well, 100% of these gases, kryptonium and xenon, which resulted in this amount of becquerels of activity released into the environment. And you see, this is the first place, yeah? And really, in all types of accidents, and in principle, in fission reactions, half of radioactivity is formed by these inert gases. Fortunately, they are mostly short-lived. Yeah, short-lived. If you look here, you will get that in several days they disappear completely. Fortunately, yes. Then next row belongs to iodine 131. And you see this quite large amounts, yeah, and here also values is very large. So this is a first point why iodine was important radioisotope. And second, I don't know about your knowledge, do you know about it or not? Because this is for doctors and biologists. Iodine is consumed by our thyroid gland. Well, any amounts of iodine in the environment or in food or in water are effectively absorbed by our thyroid gland. It's always hungry for iodine. This is why there is so-called iodine problem of radiation accidents when large amount of this radioisotope are accumulated in thyroid gland and results in huge doses to this small gland. And many health consequences appear because of this phenomenon. Then, well, next group, yeah, we can see these consequences here, and in red our heroes cesium-137 and strontium-90 are shown. So they are present in large amounts here. Why other isotopes here are not in red? And just because their half-lives are shorter. So 3 days, 2 days, 2 months, yes, half-lives. So soon they disappear. But cesium-137 and strontium-90 are still important many years. Next group called refractory in general, yeah. Despite their large quantities, they mostly went out in the form of these hot particles and fall down around this epicenter, not very far, in 10-kilometer zone or in 30-kilometer zone. So for global contamination, they were not important. And as these contaminated zones were limited for access of people, actually they don't play so much role in the consequences. And the last, transuranic, their amounts released are low, but unfortunately some of them are very bad in terms of biological consequences. This is why also a lot of attention is paid to plutonium isotopes, and levels and behavior are studied very thoroughly for these isotopes. So look again, yeah, and see people who are unaware of knowledge in nuclear physics and radiology also, they are scared by these things, yeah, radioactivity and so on. But actually, there is nothing specific in radioactivity. Most properties and most consequences depend on physical and chemical properties of these materials. Yeah, physical properties, are they gases or volatile compounds and so on. Chemical properties, what with which other elements do they interact chemically, and biological properties also. Do they participate in biological processes? Do we need them or not? And the last but not least, of course, nuclear properties, half-lives, and also types of radiation emitted by these isotopes must be taken into account too. But we must consider all together. All these properties are important. Now let's think about the process of deposition of soil from atmosphere. Oh, well, actually, these types are very simple and obvious. You don't need to be high specialist in this field. Well, if they are particles or even heavy gases, they will experience gravity deposition. And the larger, the heavier they, the more effective is this deposition, and the closer to epicenter they will fall down. Then important is the process of wet deposition with precipitation. Yeah, the rain and other types of precipitation, even smokes, even fogs could be effective in these depositions. Just there is washing out. Well, because of presence of this wet deposition, because of different climatic and weather conditions, we can have complicated pattern of depositions after such events. And we have spots, yeah, deposited radioactive materials because of climatic conditions. And the last is dry deposition, so-called dry deposition. Actually, this is just a process of adsorption of these materials from atmosphere, from air, on different surfaces. on any underlying surfaces. It could be vegetation, it could be soil, it could be even water. Yeah, there could be this process of capture of aerosols and gases by underlying surfaces. And the more complicated is the surface, the more effective is in absorption and filtering of these radioactive clouds. The better, the more effective will be this deposition, of course. All right, so we can model in principle these processes, forecast them, and calculate patterns of depositions and fallouts and degrees of radioactive contamination of territory, maps of contamination. Right, so when radionuclides appear on the surface of ground, on soil or on vegetation, they are already here on the soil, yeah? And from this point, we can already model their further behavior, and we can quantify their amounts easily. So usually there are two basic indexes, quantitative indexes, used for estimation, for description of the levels of radioactive contamination. You see that here, yeah, the first one is called specific activity, or in English literature it is often called activity concentration. Very understandable value, yeah. Activity is measured in becquerels. 1 becquerel means 1 decay per second. And specific activity is correspondingly measured in becquerel per kilogram or becquerel per liter and so on, depending which media we consider. And the second index used for these purposes is called surface contamination density. So this is kind of volumetric index. This is surface area index. And it is especially necessary in radioecology, which study large territories potentially contaminated with radionuclides, when we talk about large areas. This is why for surface contamination density, usual unit is Curie per square kilometer. Curie is also a unit of radioactivity, but it is much, much larger than becquerel. Yeah. There is a way of conversion from specific activity to surface contamination if we understand how our radionuclides are distributed in soil, in ground. So imagine we have, well, soil contaminated with radionuclides, yeah, and they penetrated to some depths. So we can consider such column containing radionuclides. For this piece of soil, we can find specific activity in becquerel per kilogram. And now imagine that this layer is large, yeah, and we can calculate all amount of radioactivity inside of this layer, integrating by surface, right? So what do we need for this? Actually, formula is simple. If this layer has a depth of h, yeah, this one, h, depth of Arab layer usually, oh, well, just a layer considered. And we know density of soil. This is very simple formula for conversion between specific activity and surface contamination density. Right. Usually at this point, I ask my students to use this formula for conversion and solve simple problem. simple problem. I'm not sure how well how ready are you now for these calculations. Maybe to save time, I'll ask you to do it at home, and tomorrow we will check. Okay? Copy this problem. Well, you know, we have this online course, and this is just lectures, and you understand very well that just listening to something is not as effective as when you do something yourself. For example, simple calculations. It will be much more effective. So, I have the answer actually here, but I will go beyond. Okay, something in Spanish. Hope it means that you will consider it at home. Right, the last part of my today's lecture is about mobility of radionuclides in soils. Right, so our radionuclides appeared first in atmosphere, and now they are already on soils because of these processes of deposition. What happens to them in soil? This is a very large question and very actually difficult question. Soil is one of the most complicated media on the earth. And well, it is complicated itself. And now we have our radionuclides inside of it. They start some interactions. And this is like this complicated dancing. Consequences depends on these dances. What are they? What are properties of soil? What soil do we have in our place? And what are our radionuclides which are deposited? What are their chemical properties? What are their state and releases and so on? So in every given case, specialists need to consider everything from the beginning to understand and forecast behavior of radionuclides. But of course, general irregularities are known today. And to understand these irregularities, we must consider these two dances. And first is soil. This slide shows some properties. Well, it is like a definition of soil. And really it is complicated because it participates in many functions. It provides a lot of services. Then this is heterogeneous. Water, for example, water bodies are much easier for understanding, for modeling of transfer of different substances in water bodies, but not in soil, which is very much heterogeneous and large problem. It is open system. Yeah, there is exchange by material and energy with other compartments in the environment. So there is no equilibrium. There are always some ongoing processes in soil. And well, there are 4 phases inside of soil: solid, liquid, gaseous, and living organisms. And they all are inside, interact, and participate in all these processes. Soil chemistry is one of the most complicated sciences. And radionuclides in soil is also a very difficult thing. I always tell to my students that this is really difficult. but we understand that you are in physics, not in environmental sciences. Yeah, you are not specialists in soil sciences and so on. But nevertheless, some common properties are understandable. So, which properties are especially important? Considering these four phases in soil, we know that there is solid phase. It is formed by minerals, right? There are different types of minerals, primary and secondary, which were formed during weathering of soils and rocks. Well, this solid phase depends, of course, on composition of these minerals. And absorption properties of soil, for example, depend on which minerals are present there. Then a second important property of soil, our characteristic of soil, is called granulometric composition. This clever word, but it means very simple things. A solid phase of soil consists of small particles, yeah, and they could be of different sizes. So there are different classifications on this granulometric composition. This table is just example. You see, we can have different fractions with different size of particles, and actually different soils, of course, they include all fractions, but in different proportions. For example, sandy soils will have a lot of sandy particles of these sizes, yeah, and a bit of small particles. Glee soils will have a lot of small particles, thin seals and so on, and a bit of large particles. So composition is always different, and there are methods to classify soils in these different types according to granulometric composition. A bit later, I'll explain why it is important which size of particles are present in soil. And the third property of solid phase in soil is the presence of organic compounds, not only non-organic mineral compounds, but organic. Well, we understand what are they, yeah? Humus, residues of dead plants and animals, which are decomposed by bacteria in soil, well, different organic molecules are present there of different size, and also different soils could be rich in organic part or poor in organic compounds. And then liquid phase, which is called soil solution. So look, this picture illustrates well how it looks like. There are these small particles which usually join into such soil aggregates, and between them there is soil solution, and also in some places there are bulbs of gas inside of this aggregates, or maybe in soil solution also. And this is like, I don't know, imagine radionuclide inside of this system. Yeah, it is like a huge city with large buildings, and small individual nuclei travel inside of this system. This is our radioisotope, one atom of it. And then it's important what will happen to it. Will it find dwelling? Will it be absorbed by some part of soil? Or maybe it will stay in liquid phase in soil solution and continue traveling with this soil solution deep in soil or horizontally in landscapes. Yeah, I mentioned already gases, soil air. Right, and the last, there are living organisms. There are some large organisms, not many of them, maybe microorganisms, and there are huge amount of microorganisms, bacteria and so on, which participate in all processes and influence on all chemical and biochemical activities in soil. So this is very living system, very active system. because of this complicated structure, soils have a really huge sorption potential. Due to this, we can use soils for growing our plants, crops, and so on, because soils can absorb and trap necessary elements, nutritive elements, first of all. And the more fertile is soil, the larger is its absorption potential. But for soils, it doesn't matter. Are materials nutritive? These elements, are they nutritive or hazardous? It means that for radionuclides, soils are also very effective absorbers. So when radionuclides fall on soils, they became accumulated by soil, accumulated in large amounts, and very, very tightly held by soils. So we have such a phrase that soil works as a depot of technogenic radionuclides. It means that they stay in soil, yeah, and they start their further movements from soil into plants and animals. Very important is this distribution of radionuclide between solid and liquid phases. If they appear in solid phase, yeah, I will return inside of these aggregates or inside of particles or firmly tied to the surface of these particles, they don't move, right? But if they stay in soil solution, they can easily move to other locations. So, high sorption of radionuclides in soil have positive and negative consequences. You see negative consequence that in this case we will have long life tradition soils. Radionuclides are in soil and it's impossible to clean soil of them. So contaminated territory will stay contaminated long time. Till because of radioactive decay and because of environmental processes, concentrations of these radionuclides decrease to safe levels, down to safe levels. But from another side, this high absorption is good phenomena because when they are trapped in soil, they don't travel to other territories. And other territories stay non-contaminated, and it is true both in horizontal direction and in vertical profile also. So migration of radionuclides down to underground waters is very, very limited. Remember these nuclear tests 50, 70 years ago already, yeah, most of them were 70 years ago. So during these 70 years, migration of radionuclides in soils, in untouched soils, which are not ploughed, which are not used in agriculture, is about 5 centimeters. 70 years, vertical migration is only about 5 centimeters. Most of them stay in 1 to 2 centimeters upper layer of soil. This is poor soil. So, and you see the consequences, we have low transfer of radionuclides to plant, to underground waters, and so on. Well, considering behavior of radionuclides in the environment, we always care about their mobility. Yeah, what influence on mobility? There are two terms used to take account of different processes explaining mobility. The first process is just mass transfer. Yeah, just mechanical transfer of radionuclides in different directions. This is called radionuclide migration. This transfer could be vertically or horizontally or to other compartments of the environment, from soil to air or to water and so on. And the second term, radionuclide behavior, means that there are a lot of different physical chemical transformation of radionuclides when they in soil or well just in other media also. And if we have chemical people in our audience, they will understand very well how important and how complicated are all these things. And as soil is such active media, all these processes go uh, in direct and reverse direction. Yeah, so there is sorption and desorption and so on. And even biota participate in these processes also, and all of them influence on mobility of radionuclides. So mobility of radionuclides in soil can change in time. And here we distinguish primary and secondary processes. And well, if I can say so, it can change in space because we have some vertical transfer and horizontal transfer. Talking about primary processes, what are primary processes? Just they appear very soon after deposition of radionuclides. As soon as they touch soil, also it's interesting. Actually, when radionuclides fall down from atmosphere, it doesn't mean that they meet soil immediately, because usually our soil is covered with vegetation. Yeah, but nevertheless, one moment they will reach soil and this primary process will start. And here, remember that tango dancing, radionuclide's properties and soil's properties will influence on consequences. What we can tell about radionuclide properties which influence? Everything is simple. There are chemical properties. And finally, when we think about mobility, we think about distribution between mobile and not mobile form of radionuclide. So chemical processes influence on it, of course, and just the place of this element in periodic table as a chemical properties. Then second group of properties, this state in release, yeah, was it originally gas or aerosol or solid particle and so on. So, for example, imagine aerosol particle. It falls down on the soil, yeah, and it is small, but still there are hundreds and thousands of atoms in it. So it means that not all radionuclides from this aerosol particle will immediately participate in processes and interaction with soil. It will take time for the dilution, different exchange processes and so on. If we imagine solid particle, fuel particle, it is even worse because they are really large. These are examples, microphotos of hot particles around the Chernobyl epicenter. You see, they are like, I don't know, meteorites, yeah, with very complicated structure. And in some places, somewhere inside, there are radionuclides. Usually, by the way, hot particles are sealed. They like ceramic matrices, and radionuclides are arrested inside. With time, because of leaching, with time, when they stay in soil years, there is leaching of radionuclides, and only later they start participating in the soil processes. So, mobility of radionuclides can change in time because of this leaching, as example, from solid particles, or vice versa, there could be decrease in mobility with time because of so-called aging. aging, yeah, radionuclide becomes old and lazy to move because it finds its place in mineral matrices and is just arrested here, caught in these minerals. So time is important too. And finally, presence of different chemical elements in soil are also important because there could be chemical analogues, some elements which chemically very similar to our isotope. For example, cesium-137, yeah, and potassium are both alkali elements from the first period of periodic table. They have the same valency and other similar properties. So there is competition between them. And in presence of potassium, cesium will lose this competition. Potassium will win all places for sorption or for uptake by plants, for example. Right, our second denser soil. And that three groups of properties which I mentioned about soil influence on mobility of radionuclide. So, size of particles. How it influences size of particles. I tried to explain you that radionuclide inside of this system is very small, like individual person in a large city. Now, what can happen to it? It can find a flat in these aggregates, in these large buildings. The larger the larger particles, the lower actually surface of these particles where radionuclide can be attached, can be soaked on the surface of aggregates. So if our soil is sandy with large particles, sorption capacity is low. I think you know from your just experience from the life that sandy soils are empty. They cannot uh, catch and hold inside water, nutrients, and so on, just because of this phenomena. Large particles have small amount of positions for absorption of other uh, substances. But in clay soils, absorption capacity is very high. And in this case, our radionuclides will be absorbed, sticked to surfaces of these particles. Minerals. Also, well, properties of minerals influence on absorption capacity, and especially high absorption capacity belong to minerals which are called montmorillonites or mica, kind of mica. They are multi-layers minerals you see with such a structure of lattice. Yeah, there are layers, and between them, when our isotope appears between all these layers, somewhere here, it is arrested forever, especially cesium-137. In montmorillonite, cesium-137 is caught forever. This is a process of aging. So, mineralogical composition influence on sorption and distribution radionuclides between mobile and not mobile forms. And finally, so-called agrochemical properties of soil. This is a set of properties which influence on fertility of soil. And simultaneously, it influences on absorption capacity too. For example, just acidity, yeah? Imagine soils with low acidity and with high acidity. High acidity will increase dilution of our radionuclide, of any substances. In this case, radioisotopes will appear in soil solution mostly. Organic matter. Organic molecules are able of forming large complexes which also trap radionuclides or other non-organic materials inside of these large molecules. So they absorb them and also hold. And well, similar speculation could be done about other properties of soil. And in general, poor soils have low sorption capacity, but rich soils are very effective in sorption of both, remember, nutrients and bad compounds like radionuclides. So these are main dependencies. And the last here, environmental modifiers, just different additional things in the environment can influence airlift, climate, and just human activities can also influence on absorption and mobility. Shortly, oh yeah, my time is nearly off. Shortly, I'd like to mention about secondary processes, which appear not immediately when radionuclides appear in soil, but a bit later when they reach so-called quasi-equilibrium state. And here there could be, you see, vertical and horizontal migration. And there are processes, physical processes in soil leading to vertical migration, like convective transfer with water up and down, capillary transfer, or just gravity transfer with water. There could be diffusion, known phenomena very well, yeah. Also, there could be biological transfer with plant root systems, for example. Also, small animals in soil. And human can do something, can plow soils or use soils for some constructions, move them from place to place. And horizontal migration. Also, processes are understandable: wind, water transfer, biological transfer with different animals, and again, human activities. So, you see, these are a set of processes which appear in soil with our radionuclide. Um, I also prepared some curious examples, but I think I'd better leave them maybe for the beginning of tomorrow lecture because of lack of time. Because maybe you have a couple of questions. Can agriculture serve as a fixation? Um, well, no. Active agricultural practices increase mobility of radionuclides. So the best way to stop any practices and don't use contaminated soils. But when we are still interested in agricultural activities, we can apply some specific countermeasures and improve the case, and really we can work on fixation of radionuclides in soils. I will tell you about these measures in my lesson 4. What kind of law does meditation source follow, taking into account the influence of the wind? Oh, well, there are such calculations, there are such models um, describing this transfer by wind. So it is another field, yeah, consideration of atmospheric transfer, Gaussian law of distribution, and so on. There are models. They, by the way, intensively used when they model, you know, at how it's called, before construction of nuclear installation, they develop a plan of all possible situations, and they model also potential accidents with release of isotopes into atmosphere, for example. And there are special models and special codes for modeling on this transfer. Okay.
Okay. Thank you, Professor Udalova. I don't know if there are another questions. I think not. Okay. Thank you again.
Well, I think you have 5 minutes for the break.
Yeah. So, perdón, ¿vamos a parar la grabación o vamos a continuar con la grabación para el siguiente módulo? Ok, creo que vamos a... sorry, I think we are going to stay. So, if the second one is Professor Melnikova, right?
Yes, good afternoon. I can start. But now you have break, small break.
Yeah, I think we can
I don't hear you.
start. Sorry, now?
Now I hear.
Okay, so I was saying that we can wait for maybe 5 minutes, and
Oh,
after that we continue.
okay.
Okay?
I wait.
Okay.
I wait for 5 minutes. Okay.
Okay. Zinkova, are you there?
Okay. I think I can start.
And we can start
So,
again.
my screen. So, I hope you see my presentation.
Yes.
Yeah, thank you. Thank you. Okay. Um, today's first part on my lecture related to radiolysis of organic compound. And I will speak about the common information of radiolysis of organic compounds. So, the first. Many organic substances are widely used as extractants, dilutants in nuclear fuel reprocessing technology. Some aromatic compound, due to their high radiation resistance and as promising coolants for nuclear reactors. Therefore, knowledge of regularities of radiolysis of these systems is very important for predicting their behavior under various technological conditions. Um, it should be noted that the determination of the entire set of radiation chemical transformations in organic liquids leading to the accumulation of the end products is a rather difficult task due to the wide variety of reactions involving active intermediate particles, such as ions, then electrons, and excited molecules. During the radiolysis of even the simplest organic compounds, such as methane, CH4, or ethane, C2H6, and etc., more than 10 compounds are formed. The overall picture of radiolysis can be complicated by the fact that some primary stable products have a higher reactivity, with respect to active intermediate species than the initial molecules. So, um, now these three principal mechanisms are adopted to interpret the formation of radiolytic products. These three principal mechanisms are free radical mechanism, then excited state mechanism, and interaction with solvated electrons. The presence of atmospheric oxygen, different impurities, scavengers, as well as the type of solvent, type of radiation, then dose and dose rate effect on the mechanism of radiolytic reaction. And now I shortly describe each the mechanism. So I start with molecule excited mechanism. This molecule excited mechanism in which excited molecules interact either with themselves or with other molecules to produce radicals and radiolytical products, excuse me. Next mechanism, free radical mechanism, in which the free radicals form due to de-excitation of the excited molecules interact with solute or with the solvent molecules or with each others, or degradation occurs to produce um, radiolytic products. And the next mechanism, solvate electron mechanism, in which solvated electron interact with reducible centers such as carbonyl groups to reduce them to alcoholic groups or to react with the positive molecules to produce to reduce higher oxidation state metal ion to low one. So uh, the three mechanisms participate simultaneously to produce radicals and radiolytic products, and the predominant one depends on the nature solvent, then nature of solute, presence or absence of oxygen, uh, absorbed dose and dose rate, temperature and pH of solutions. To explain the influence of these parameters, we used our own research work. These studies are related to of radiation chemical transformations of micro impurities of organochlorinated pesticides in model solution and food products. And also we use the study of radiation stability of organochlorinated pesticides such as alpha, beta, gamma, hexachlorocyclohexane in composition of the pesticide preparates hexachloride dust. So let's consider different parameters. And I start from the nature of solvent. The nature of solvent depends on whether it's polar or not. Polar solvents facilitate the rapid information and stabilization of solvated electrons that enable them to be more efficient for reduction, such as in isopropyl alcohol. According to research, it is known that if radiation chemical reaction occurs in solution of a substance, then the nature of the solvent can significantly affect its mechanism. Radical or with participation of solvated electrons. The initial stage of which includes the excitation and ionization of molecules. The ionization of solvent molecules under radiation proceeds more easily if solvent has a higher dielectric constant. In addition, the degree of solvation of solvent molecules has a great influence on the formation of active sites. The radiation chemical yield of solvated electrons in polar medium is higher than in a non-polar one. The process of solvation is accompanied by the release of significant amount of energy, which can be spent on the ionization of new initial molecules, which leads to a further acceleration of radiation chemical reactions. Let's look at the effect of solvent polarity on the radiation stability of organochlorinated pesticide solutions. The figure shows the diagram of distribution of radiation chemical yield in logarithm scale for various concentration of organic chlorinated pesticides and solvents. So what is the concentration? Concentration 0.01 ppm, 0.1 ppm, and 1 ppm, or microgram per milliliter. You see these different pesticides, alpha, gamma, hexachlorocyclohexane, then DDT, the famous pesticides, and its metabolite DDE. And also we consider different the solvent hexane. These graphs A and 2-propanol graphs B. As can be seen from the diagram describing the change in radiation chemical yields of each pesticides, depending on its initial concentration in 2-propanol and hexane solutions, differ from each other. This is apparently due to above reasons, namely the difference in the values of the dielectric constant, then radiation chemical yields of solvated electrons and radicals in hexane and 2-propanol. And you see this value in table. So dielectric constant for hexane equals 1.9 to power 25. But for 2-propanol, 15.3 to power 25. Difference is order. So the yield of the radiation chemical yield of solvated electrons. R2-propanol 1.3 molecule per 100 electron volt, and hexane 0.12 molecules per 100 electron volts. It's also known from the literature data that under irradiation, the total radiation chemical yield of radicals in hexane is 5.67 molecules per 100 electron volts. And to propanol, 6.81 molecules per 100 electron volts. Thus, it can be assumed that the conservation or transformation of organochlorinated pesticides under radiation into propanol is a result of dechlorination reactions by radical mechanisms and with the participation of solvated electrons. And in hexane, to a greater extent by the radical mechanism, since solvation of electrons it is participally absent in comparison with 2-propanol. So, next parameter, the nature of solid. The nature of solid affects on the direction of radiolytic mechanisms. If solid scavenge electrons, other mechanism will be effective for affecting on the solvent. And the scavenging solid will be reduced. If the solid S, yes, S, is ketone, electrons can be scavenged and free radicals may be scavenged also to produce to radiolytic products. So let's consider oxygen. So oxygen has an important role with hydrogen radical to form H2O radical, reaction number 1. And this changes the nature of radiolytic reactions to produce different radiolytic products. The nature of hydrogen radical is reduction, whereas that of H2O radical is oxidation. The present solvated oxygen can scavenge easily the solvated electrons and to form ionous, O2 of O2, which it is reaction number 2, which reacts then with the ionus of hydrogen to form the H2O radical, which has higher oxidizing tendency. Instead of reducing by solvating electrons in case of absence of oxygen. As a result, different radiolytic products may be formed due to different actions of formed species in absence and presence of atmospheric oxygen. So, um, again about oxygen. This slide presents the results of study of the effect of oxygen of decomposition of organochlorinated pesticide when irradiated with gamma rays. So, prepared solutions of pesticides were divided into two parts. The first part, initial solutions, was studied in an air-containing medium. And the air was removable from the second part by purging with oxygen-free nitrogen. Blowing with nitrogen gave a sufficiently complete purification from oxygen, which did not require subsequent pumping out of the gas. Since nitrogen is not with respect to most radiation chemical system. So, on the slide you see the different graphs. I explain what do you see, okay? Because some names on the slide I give on Russian, okay? So you see different blocks, white blocks and, for example, gray blocks, yes? White blocks correspond to results presence oxygen, and gray blocks corresponds to results without oxygen, absent oxygen, yes? So, and usually the first two blocks it is results in hexane, and second two blocks there are results in 2-propanol. And you see results for DDE, graphs A, gamma HCH, graphs B, HCH, I remind you, hexafluorocyclohexane, and alpha HCH, graph C. This solution we irradiated a dose of 10 kilogray with a dose rate of 2.33 gray per second. As can be seen from figure or from slide, yeah, the presence, oxygen in irradiated solutions had an impact on degradation degree of organochlorinated pesticide. Despite their low concentrations compared to oxygen, the diagrams show that degree of decomposition or degradation degree of pesticides increased after the removal oxygen from solution. You see gray blocks, sometimes almost two times, two times. And it was more significant for solution in a polar solution, such as 2-propanol, such 2-propanol. You see this second two blocks here, here, and here. Um, Obviously, this is due to the fact that in the process of radiolysis of initial solution of organochlorinated pesticides, the radiation chemical yield of oxidation products of 2-propanol molecules equals approximately 20 molecules per 100 electron volts, is greater than oxidation products of hexane molecules. And here, approximately 8 molecules per 100 electron volts per electron volts. Next parameters: dose rate and dose. The dose rate and absorbed dose effect on the radiation chemical yields due to rapidity of some reactions than others. For example, the physical and chemical changes are more effective at high dose rates due to their short period of reaction. Whereas the chemical stage reactions are effective at moderate and low dose rate. The variation of absorbed dose and dose rate interprets the different values of radiation chemical yield obtained during radiolysis of the same medium. So, again, my examples. Let's consider the effect of dose rate in range. You see dose rate range 0.0083 and 1.35 gray per second. We consider the effect of dose rate on the degradation degree of DDE model solution. The data presented in the slide indicate that dependence of the degradation degree of pesticides in this range of dose rates of gamma radiation is complex. You see these graphs. The graphs shows that the degradation degree of DDE with increasing dose rate first increases. You see the first part of these graphs. Then passes through maximum. Maximum corresponded to dose rate of 0.23, 0.43 gray per second. And then the degradation degree of DDE decreases. The nature of the dependence of degradation degree on the dose rate is preserved for DDE is solvent of different polarities and doesn't change with change in concentration of initial substance. Effect obtained in the range from 0.0083 to value with maximum degradation degree. So I remind you, the maximum correspond to dose rate 0.2, 0.4 gray per second. Apparently has the following explanation. If we assume that in the region of low dose rate, the radiation chemical yield of radicals should be lower compared to the radiation chemical yield in the range from 0.2 to 1.35 gray seconds. Then this leads to decrease in the number of reactions as well as their competition with each other. This gradual increase in solutions, reaction number one, you see this reaction number one, with this solvent radicals, C14H9 chlor 4, it is DDE. Now, this reaction has predominant reaction, which according our data, leads to increase the value of degradation degree. With further increase, the advantage probably remains with other reactions. Reaction number two. This circumstance explains the degrees in degradation degree observed on the curve of the figure. Decrease. And it should be noted that solutions were irradiated in presence of dissolved oxygen, which reduces the decomposition of pesticide, since competes with it in reaction number one. This is especially noticeable at a low dose rate, range from 0.0083 to 0.4 gray per second, when the energy entering the solution may not be enough to completely consume consume dissolved oxygen in the range of high dose rate from 0.4 to 1.35 gray per second. Dissolved oxygen is obviously consumed at the initial stage of radiation and has no further effect on the radiation chemical process. About the absorbed dose, yes, absorbed dose. It can be seen from the slide that with increase of radiation dose of pesticide solutions, the degree of their decomposition increases significantly. So, I explained this slide. So, you consider the degradation of DDE, and the white block correspond to those of 1 gray, and gray block correspond to those of 10 gray. And then again, the first two blocks, uh, hexane solution, and second two blocks in 2-propanol. Um, at the same time, I explained further, the influence of the concentration of initial pesticide and the polarity of the solvent on the degree of the radiation chemical decomposition, which is preserved when pesticides are irradiated both at dose 10 kilogray and a dose of 1 kilogray. Is noted. Now, uh, at high values of degradation degree, which were obtained for a dose 10 kilogray, I remind you, gray block is with of 10 kilogray, this effect is more significant, as the diagrams in the slide clearly show. So, next parameters, temperature and pH solutions. The difference of working conditions of pH and temperature effects on the radiolytic mechanisms and reactions. For example, at low pH value, the H plus acts as scavenge for electrons to produce the hydrogen radical or facilitate the ability of oxygen molecule to scavenge electrons to produce um, hydrogen peroxide, H2O2. The temperature has an important effect on the rate of radiolytic reaction, like a normal reaction. Reactions, yes. The rise of temperature increases the radiation chemical yield due to rise of energy levels of solute and solvent. And as a result, less energy will be required for production of inner path and either excited species. So I give you definition of homolysis. Homolysis of excited molecules um, forms free radicals that are very reactive. They have unpaired electron and enter in many reactions in a radiated medium. The free radicals may react with stable molecule or other radical or ion forming intermediate or final products. Uh, Sometimes scavengers are added to react with some certain primary radical species. Some scavengers are mm, specific for certain species, such as electrons. This can be utilized to measure the quantitative formation of these species. Other scavengers are less specific. At concentration lower than 2 power negative 4 mole per liter, scavengers will react only with some diffusion species. Scavengers of concentration of more than 2 power negative 4 mole per liter will react with all diffusion species formed. Excuse me. High concentration. High concentration correspond concentration over zero point 0.1 mole per liter. High concentration are used to scavenge the primary species and inhibit the intermediate reactions. Sometimes certain scavengers are added to remove certain primary species to prevent some reactions and to let another to proceed. Sometimes in the excited molecules, the energy is absorbed at a certain location and the effect appears at another stable site. So, this slide is presented the mechanism of dechlorination under irradiation of hexachlor cyclohexane, namely gamma HCH into propanol with participation only free radicals, only. So you see the first reaction, and the first reaction you see the excited 2-propanol, and these molecules decay into radical. Then this radical can react with initial molecules of pesticides, and in case reaction number 2 um, you see the nuclearination products and pesticides radicals. If you consider the reaction number three, you see that products of these reactions, again, pesticide radicals, yeah, and chloride ions. Um, so these diagrams, these schemes, yes, shows that the free radicals formed as a result of gamma exposure to the solvent initiated the chain process of gamma HCH dechlorination. In this case, they interact, they both solvent molecule, reaction number 4, uh, so, and pesticides molecule, reaction number 6. And you see the chain process dechlorination. Um, um, a next slide related to solvated electrons. Um, I say some words about these electrons because we consider the hydrated electrons in previous lecture. Um, Solvated electrons are the very active species that form during the radiolysis. Um, on the slide is presented different properties of solvated electrons. But I stop only one properties about lifetime. You see that the solvated electrons have a period life more to power negative 6 seconds. And I also want to say that uh, the mobility is lower than those of electrons of metal conductors and higher than negative ions. So, in analysis of the experimental material of different, materials on the radiolysis of organic substance, shows that the composition of products of radiation chemical reactions depends on the type of radiation. Um, mm, but I want to say that in radiation chemistry, um usually use the gamma radiation and the electron beam. Then, the nature and structure of organic compounds, and the last, their state of aggregation. Aggregation. So, um, all products formed during the radiolysis of any organic compound can be divided into three main groups. The first group, products of the extraction of organic molecule. Second group, internal convention, products in which the carbon chain of resulting compound contained the same number of carbon as the chain of the pattern parent compound. And the last group, it is complication products of the molecule. So I explain these products a little bit. Okay, uh, let's look at specific example. Before us are chromatograms of hexane solution of alpha HCH before and under irradiation. Alpha HCH is organochlorinated pesticides. Its full name's alpha hexachlorcyclohexane. As we can see in figure A, there is only one peak on the chromatogram, which corresponds to alpha HCH. You see the alpha ACH and in Russia equivalent alpha GHCG. Excuse me. So it is alpha HCH. And also you see a few more small identified peaks. In figure B, a lot of peaks appear on chromatogram, which are located both before alpha HCH and after alpha HCH. Typically, the decomposition products of the initial compound have a shorter retention time. That is, their peaks will be in front of the original substance, initial substance. On the chromatogram, we see the pentachlorcyclohexene. You see this formula, which is a dechlorination product of alpha HCH. So, adjacent to the alpha HCH peak and several peaks identified as isomers of HCH, such as beta HCH, gamma HCH, delta HCH. All these isomers are products of inner transformation. And the end of the chromatogram. Peaks also appeared that are difficult to identify. But most likely that they are products of complications of molecules. For example, a molecule formed as a result of recombination of hexane radical and an alpha HCH radical. So, next slide. This slide shows the possible pathways for formation of internal conversion products of alpha HCH and degradation products. As we can see, the products of internal transformation are HCH isomers. It is most likely that beta, I show these isomers, and delta as also isomers, delta HCH. These isomers are formed from alpha HCH. You see different pathway, yes? So, potentially more favorable is the position of chlorine atoms in the plane of the cycle. Plane, you see this plane, yes? Plane of the cycle. In the structure of alpha HCH molecules, two chlorine atoms, I show these atoms, yes, are connected to the cyclic path XL, no, XL or perpendicular, yes, and four chlorine atoms, 1, 2, 3, 4, equatorially in the plane of the ring. The beta HCH contains respectively two axial, excuse me, axial, I don't see axial, I think maybe here, two axial and four equatorial chlorine atoms. And delta, excuse me, my my mistake. This delta HCH, this beta HCH. So, and delta HCH molecule contains respectively 1 axial and 5 equatorial chlorine atoms. That is, these molecules will be more stable than alpha HCH. And now the second part of the third lecture, you consider the radiolysis of hydrocarbons. So now I say some words about the hydrocarbons. In organic chemistry, an alkane or paraffin, and historical trivial name that also has other meaning is an acyclic saturated hydrocarbon. In other words, an alkane consists of hydrogen and carbon atoms arranged in the tree structure, in which all the carbon bonds are single. Alkanes have general chemical formula CN H2N plus 2. The alkanes range is complexity from the simplest case of methane, CH4, where M equals 1, sometimes called the parent molecule, to arbitrarily large and complex molecules like penta, uh, penta contain. Formula C50H102. So the International Union of Pure and Applied Chemistry defines alkenes as acyclic branched or unbranched hydrocarbons having the general formula CnH2n plus 2 and therefore consisting entirely hydrogen atoms and saturated carbon atoms. However, some sources use the term to denote any saturated hydrocarbon, including those that are either monocyclic, that is, cycloalkanes, or polycyclic, despite their having distinct general formula that is cycloalkanes CnH2n. In alkane, each carbon atom is sp3 hybridized with 4 sigma bonds, either CC or CH. And each hydrogen atom is adjoined to one of the carbon atoms in a CH bond. The longest series of linked carbon atoms in molecules is known as its carbon skeleton or carbon backbone. The number of carbon atoms may be considered as the size of the alkane. The alkanes have two main commercial sources: petroleum and natural gas. The alkyl group is an alkane-based molecule fragment that bears one open valence for bonding. They are generally abbreviated with the symbol for any organyl group R, although sometimes ALK. No. So, let's consider the main reactions taking place during the radiolysis of alkanes. Using N-hexane as an example. So you see the reaction number 1. When N-hexane is exposed to radiation, ionization and excitation of its molecules occur. So, and you see that from the ionized molecule of hexane, then electrons and excited molecule of hexane. So, the most uh, probably decay channels for unexcited molecules of hexane are the elimination of hydrogen or molecule hydrogen. These are the first two reactions, reactions number 2 and reaction number 3. Um, as we can see in reaction number 2, molecule hydrogen and hexene are formed. Hexene C6H12. In reaction number 3, as a result of decay of excited molecule of, or excuse me, molecule of hexane, hexyl radical and hydrogen radical are formed. Hexyl radical C6H13. Other reactions can occur, but with low probability. These are reactions number 4, 5, 6. In these reactions, radicals of different compositions are also formed. For example, in reaction number 4, you see two radicals. This radical C5H11 is pentyl and CH3 methyl. Reaction number 5, CH or C4H9 butyl, C2H5 acyl. And in the reaction number 6, you see the same radicals. It is propyl C3H7. So, next. During the radiolysis of hexane, hexyl radicals, you see these hexyl radicals, are mainly formed. You remember this reaction number 4. And then can be occur the reaction number 7 and reaction number 8. During this reaction forms the heavier end products. For example, reaction number 8, dodecane. But in reaction number 7, you see the initial molecule hexane, and you see alkene hexene, C6H12. One moment, please. Okay, I have time. So next reaction. Reaction number 9. So the each atoms from reaction I remember reaction number 2. Yeah, this atom H atom reacts with initial molecule and forms the molecule hydrogen H2 and hexyl radical C6H13. Also, the methyl radical reaction number 4, Yes, this radical is formed in reaction number 4. Reacts with again the initial molecule. In this case, forms the methane CH4 and again hexyl radical. So the small conclusion. Um, the main stable products of the radiolysis of normal alkanes are molecule hydrogen. You remember that molecule hydrogen is main product of radiolysis of saturated of hydrocarbon. Also form the saturated and unsaturated hydrocarbons of the composition. You see different composition C sub 1 or C sub n minus 1, in particular methane. Then forms alkenes Cn, alkenes C sub n plus 1 or C sub 2n minus 1, and also forms dimer C sub 2n. Ongoing from normal alkanes to branch alkanes, the radiation chemical yield of molecule hydrogen decreases significantly. For example, radiation chemical yield of molecule hydrogen in hexane equals 5 molecules per 100 electron volts. And radiation chemical yields equals 0.5 molecules per 100 electron volts for neopentane. Neopentane is branched alkenes. On the contrary, the radiation chemical yields of the CC bond cleavage products increase. So, this slide is presented the general scheme of radiolysis of alkenes. Let's now take a look at the radiolysis scheme and compare it with the radiolysis of hexane. Okay, so I have time. So under irradiation, an alkane molecule is ionized and excited. Reaction number 1. You see the ionized and excited molecules, and you see also electrons. So secondary electrons slow down and become solvated. This is reaction number 2. But we must remember, alkanes are non-polar compounds. So the radiation chemical yield of solvated electrons will be small compared to polar compounds. After some time, the solvated electron attracted to the ions. Reaction number 3. As a result of this electron ion recombination, yes, or neutralization maybe, excited alkane molecules are formed. You see this excited molecule. As a result of reaction 4 and 5, hydrogen and molecule hydrogen are formed, as well as alkyl radical in reaction number 4, and alkene reaction number 5. These reactions are more likely than reaction number 6. So next, we consider the reactions 4, 5, 6 using the example of hexane radiolysis and see corresponding to reactions. 5 reactions when forms the molecule hydrogen 5, 5. Reaction number 4 when forms hydrogen, and reaction number 6. Number of these reactions will be depends on the number of atoms in alkanes. So, one moment, please. I open this slide. So, the formed hydrogen in reaction form, you see this hydrogen, yes, can react with alkane, is reaction number 7, or alkene, reaction number 8. When hydrogen reacts with alkane, an alkyl radical and molecule hydrogen are formed. When hydrogen reacts with alkene, the alkyl group is formed again, reaction number 8. Reactions number 7 and number 8 are competed and depends on the radiation dose. The excuse me. The alkyl radical formed in the reaction 4, 7, 8, and 8 can react with the initial alkene molecule. Reaction number 9. This initial molecule and alkyl radical, excuse me. We consider these reactions using the example of hexane radiolysis. This reaction number 7 and the reaction number 9. So, I give only 2 slides and finish. So, I open all slides. Radicals formed in the reaction 4, 6, 7, 8, and 9 interact with each other to form alkane and alkene. This reaction number 10. And dimere, this reaction number 11. Hydrocarbons are also formed in which the number of carbon atoms is less than n. It is reaction 12 and 13. And you see the example of hexane. And the last slide, okay, excuse me. So I open all slides. So in addition to reaction from 1 to 13, as the decomposition of ions that were formed in the first reaction is possible. This is the first reaction, yes, and you see the ionized molecule of alkane, excuse me. Decay reactions correspond to reactions 14 and 15. You see. Then there is a neutralization of resulting ions. It is reaction 16 and 17. And as well as the interaction of radicals, reaction 18 and 19, leading to formation of hydrocarbons such as CM, H2M plus 2. Oh, but remember that M, more N, but less 2N. I finish.
Okay.
Okay.
Thank you, Professor.
Thank you for your attention. Excuse me.
No, no problem. Are you okay?
Okay. I want to speak.
Okay, don't worry. We have some minutes, a couple of minutes for questions. If someone is have a question, okay, we have the first one. Do you prefer to read it, or I will?
Our health. This question about the previous lecture, yes. When you consider the radiolysis of water, we speak about that our body consists a lot of water, yes, and therefore, when you consider the interaction radiation with our body, you consider two mechanisms. Direct mechanism, when the radiation interaction, just one moment, please, with molecules, or interaction mechanism. With the first step, the radiation interact with water, then forms the different reactive products such as ions, radicals, excited molecules. There are a lot of species, and then this species reacts with our organs, tissues, cells, and I said we have a lot of water. Therefore, in our body, one moment, please, will be an interaction, just a moment, indirect mechanism in our body. And I said also that approximately 10% damage related to indirect mechanism, and only 20% only direct mechanism. I hope you understand my answer. If you want, I answer later, okay?
Okay, thank you.
If I can add a few words to this answer, if you don't mind, Tatiana Vladimировna.
Mm-hmm.
Well, you know, health effects, first of all, depends on the dose. So there is a radiolysis process always, caused by background radiation too, and also caused by another agents, not only by radiation, but by another processes. And everything depends on the level of this, intensities of these processes. So if it's not so much, nothing bad for the health.
Я немножко не так поняла вопрос, извините. Угу, забуду.
Ну, там по-разному можно.
Да. Но я со своей стороны все, извините. Все. Thank you for your attention.
Okay, thank you, Professor. Okay, if we are ready, maybe we can move to the other speaker, the next speaker. Thank you for your question, Julius.
Goodbye.
Thanks again, Professor.
I saw during the lecture that some student raised hand. Nadia,
Yes.
I saw, yeah.
Yes, I saw a raised hand.
I guess it was question to some slide, some certain slide, maybe.
Yeah,
Well, maybe not actually anymore.
yeah, I don't remember the name, but
Nadia,
yeah.
I remember Nadia.
Nadia, okay. Is Nadia here? Pero Nadia tenía una consulta, tenía la mano levantada. No. Okay. Maybe not. All right. Is Professor Fleming around?
I'm sorry, I forget to switch on the microphones.
Okay. Hello. How are you?
Good day. I'm nice, and you?
Very well, thanks. And welcome back to our second day of the lectures. So if you are ready, maybe let me ask to the audience if they want to 5 minutes break.
Okay, waiting 5 minutes and start, yes?
Okay, yeah. Let's
All right,
do the same.
I try check the presents, how it's working.
Great. So see you in 5 minutes. Thank you. All right, we are ready for our last talk by Professor Fomin. So, Professor Fomin, are you there?
Yes, I'm ready. And we can start.
Yes, please. You can
All
start.
right. At first moment, I'm very glad to see you today on my secondary lecture. At first, I want to check the some our systems. I hope you heard me and see the presence and all slides will be changes. Yes, no problem.
Yes, everything perfect. Everything
All right. Uh, and let's begin. Today we discuss some many important things about the construction of research reactors. We start our discussion from the some classification of research reactors which use it in the world. Next, we discuss the so think as thermal schemes, which is used for determine some many important parameters for reactors, which for research for reactors for NPP. Next, we discuss the construction of and different classification about circulation pumps. It's I give you some basic constructions which use it on different NPP. And in the end of our lecture today, we discuss the materials and the constructions of pipelines, which use it, of course, in all our research reactors. And first, classification, and we start from the classification of research reactors. Usually, when we say about the research reactors, we must understand the first and the big classifications about which telling in the world. It's they have the very simple principles, and it's usually constructions which we can separate as a single circuit NPP, double circuit, and three circuit NPP. I'm sorry, sometimes I will be tell NPP because I read these courses for different our students. But these classifications working, of course, and the for research reactors. Which differ between these classifications for one, two, and three circuit NPP. And when we say about usually common constructions of research reactors, we must understand that usually it's construction which have only one circuit NPP. In the most different, in the most variants of constructions, it's the one circuit NPP. Sometimes we can find the double circuit NPP. It's usually the research reactors of the tank type, and the last and the so rare construction in the three circuit NPP. It's usually research reactors with which working with the very aggressive materials. For example, of these research reactors, so I can say that it's the reactors of fast sodium 350, which now shut down, but it's a very famous reactor because he is a play role as NPP, as the experimental reactors. He used it for generate hydrogen, and he used it to distillate seawater. And of course, it's very big spectrum of all scientific work which we have in our life and which working for all reactor types. And the next classifications and what the first moment about which I say about these classifications. You see that I use three different classification, which I think is most important for all research. The red parameters is the classification of pumps, and the yellow is so medium stage, which we can use it for research reactors and for nuclear power plants. And we start from the first green stage. It's the neutral stage. Divided all reactors, the thermal, intermediate, and the fast neutrons. If we say, for example, on NPP, usually for NPP we use the thermal reactors because if you know the some physics process which give us the fission reactions, They consist from some energy from neutron which interact with our nuclide, and usually for fission reactors for our common fuel, which is the uranium 235, uh, he interact in the thermal region and have the fission process. But for research reactors is most interested the second and the third spectrum of neutrons, intermediate and the fast neutrons. Why? Uh, Usually, when we say about the production of some radioisotopes, for us interested the intermediate spectrum for neutrons. Why? Because in these regions we have the some structure as resonance, and it gives us the some interval of energy in which we have the very high probability of any type which will be maybe interested for us to produce some isotopes. If we say about the fast regions, each region is very interested for us in the way of burn up spent fuel, and it's the so-called the productions of new secondary fuel. And for this purpose, for productions and for burn up, usually we use the fast spectrum of neutrons. Uh, in the different situations, usually all research reactors for more interested for us is the intermediate spectrum for any reactions. Next step is the parameters and type of steam turbine. Of course, for research reactors, we don't say about the steam turbine because usually if we say about we use the steam turbine, it means that we produced electricity. But as I say on the last lecture, uh, many research reactors not use it for production electricity. Of course, sometimes they use it for produce the some part of heat, which we can use for different purpose. But this classification on the saturated and superheated steam, it's not effective when we say about the research reactors. Next step, the principle of uses is the stationary, transportable, and transport. Uh, Many types of research reactors, of course, it's the reactors, the stationary. And stationary, it means that we build reactors on the some place, and all his life he stand on this place and working operations, and after decommissions, um, after he live all the life. Transportable, it's reactors which we can transport from one point to different point. Um, Maybe most famous these reactor types is the reactors which we use it for some cosmic industry, and we send this reactor on the orbit of our planet. And in many cases, of course, these reactors use it as sources of energy for working any satellite for our planet. And the last is the transport classifications. When we say about transport, usually when we say about transport, it's the reactor which uses it to move some machines. The most famous example is nuclear navy, and of course it's the nuclear submarines and icebreaker fleet. But icebreaker fleet we have only in Russian federations. Nuclear submarines, it's a very secret information, and of course we can discuss it. Next stage is the parameters and type of the coolant, and we can use it the different coolant and for the research reactors. Of course, we use it all this coolant type. It may be gases, it may be some liquid metal, organic. It may be, for example, some liquid of fission materials. It may be in the water of the pressure, under pressure, in the vacuum, and the differ. And usually, all research reactors, many research reactors, working with a different coolant. Why? Because, as I say, usually all research reactors is needed for us to build the NPP. It's one of the steps of increase the power of all nuclear engineering. And of course, all these new coolant, fuel, construction materials, we must research and check how they parameters and how these parameters will be changed in all reactor life. And of course, for this purpose, we use a different coolant. Next is the reactor design, tank, channel, pool, and from the last lecture, I repeated all these all these constructions we use it, and in the most situations it's the pool constructions. But today I told you about the tank reactor type. Why? Because the main difference between the tank and the pool reactor consists in only one important element in the reactor vessels. And of course, it's most interesting for us look in the reactor vessels. I think so. Because in the pool, it's only the pool with the reactor core. Our pool they plays the role of the vessels, and usually it's pool located in some inside of our pool. We located the water, and we see the many interesting things and some part of the thing I show you today, and of course it's the one of the famous things which connected with all research reactors. And the last is the so-called the pair of the coolant moderator. It's water-water, gas graphite, water graphite, and different combinations. Uh, they show us which medium we use it as a coolant and is a moderator. Of course, sometimes, usually, it's more comfortable for us use one medium in both this role. But sometimes, if we say, for example, in the research assemblies, which don't have the some power, level power, and of course they don't produce the heat. In these situations, we say about only the moderator, and we don't use the cool. That's all. Next subject is the so-called the thermal schemes, which are used for all projects. The schemes for conventing and using the thermal energy of the working fluid in the different our facilities is the called the thermal. It shows us the equipment by means of which the thermal process are carried out and combination of this equipment into some single installations with all connection line. Of course, usually connection lines, when we say about connection lines, we mean the pipelines. And these thermal schemes deleted by two big and different schemes. It's the basic schemes and the complex schemes or detailed schemes. Uh, and you see the example of basic schemes. I'm sorry, I show you the basic schemes of PVR reactor types. Sorry, it's a fast sodium reactor types. Unfortunately, I can't find the schemes for some concrete research reactors. But in the basic, you must understand the basic diagrams. You can show as the one figure. But when I say about the complex schemes, you see that it's a very big number of some documentations for some draw specifications and other document. And in the real life, we cannot show it because it's very big amount of paper. The basic schemes or the basic diagrams, it's the main design and technological diagram of the our nuclear facility for any type of this facility. The choice of the type, drawing up the basic thermal diagrams and its calculations, is one of the most important stage when we design our nuclear facility. In this stage, we must determine the efficiency of all our construction elements. And of course, the assessment of the thermal and neutron efficiency is based on the some thermodynamic efficiency of the thermal energy conversions. Some depends from the thermodynamic cycles and of initial parameters of our medium, which will be located inside of our research reactors. Usually, when we say about the basic schemes, The basic schemes include only the main equipment. It's reactors. Uh, it's the main in the accelerator heat exchanger. It may be I'm sorry. In this, we of course include our circulation pumps and the different elements which include in our schemes. The composition of equipment in the primary determined by the type of the technological parameters, the type of coolant, and the medium which will be used for our reactors, which will be designed in this stage. To achieve the great clarity, the schematic thermal schemes does not show the some equipments, units, and the different systems which have the same functional purpose and operate in the same parallels. For the same reasonable some duplicate pipelines, some switching and auxiliary connections pipelines, fittings, valves are not applied on these schemes because it's not required for us. The complex schemes is the show all equipment, all units, all systems, systems which working, backup, emergency systems, some auxiliary systems, and of course the pattern draw with all this line, all connections, all contours, all parallels, and all elements. The main and backup reinforcements, of course, is applied. The drawing of the complete thermal schemes is accompanied by a specification linked by the type, number, and some technical characteristic of our equipment. The complete thermal schemes, its specification characteristics is have the reliable level of some nuclear installations. A complete thermal schemes is developed after drawing up and calculating the basic thermal schemes and after choosing the main equipment, so some resolving issues about its redundancy and issues related by some ensuring reliability. And this schemes is the last stage, and this is documentary which will be used to build some reactor, for example, research, NPP, and different nuclear facility. For this purpose, we use only the complex schemes. Uh, Basic schemes is needed for us to improve our basic purpose and checked the main interactions for all our main equipment. Next stage is the design of the reactor. And we start to describe the different constructions. Of course, I will be discuss the constructions of 10 characters, as I say, but all the things about which I will be tell you about the 10 character types, it's working on the pool reactor types for it's working for the fast reactor types, but we have the one difference, as I say, we have some vessels, and I think the describe of constructions of some equipment which located inside this vessel is the main important thing to understand for understand the construction not only for research reactors but and for understanding the construction of NPP. And of course, as example, I choose reactors with pressurized water reactors, and we will be describe these constructions. But of course, I don't start my lecture and my presentations without the very famous uh, and effective figure and the effects. It's the so-called the emission of Cherenkov-Vavilov. You can see in this figure this effects and usually on any working NPP you can see the all blue or green color when you looked on the our reactors and when he start working and of course I can describe this effect on the Russian language because it's not so-called Max specialized, but of course its look is very great, and it's so the very famous effect which you can see on the different reactors. Of course, it's more often you see this reactor only on the research reactor because the big high of water in the pool reactor is given for us its possibility. But you can see these effects and on the PVR reactor types and on boiling water reactor types when I say about the procedure of recycling. In all these cases, we see these emissions, but of course, in all only on the pool reactor, you can see is more comfortable for your viewer, and you see, of course, in the any moment. And let's start and discuss our constructions of PVR reactor types. Because we say about PVR reactor types, it's the reactor types with the tank. For me is most comfortable say about the vessel type reactors with the pressure and or with the high pressure inside our vessels. In these cases, usually the water uses as coolant and as a moderator. Some problems or not? Sorry, I checked the connections. Так, no problems. See, you heard me and see the results, yes?
Yes, we can hear you.
Right, I'm sorry, I continue. All right, when we say about this reactor vessels, it's usually is a vertical cylindrical high pressure vessel with some lid having the connector with the seal and pipes for inlet and outlet of coolant, which you can see on this diagram here. In these constructions, it's figure I take from some research article from the Europe. And the main difference when we say about, for example, of high pressure NPP reactors, uh, usually inlet and outlet will be located on the different level on the higher for our reactors. But here you can see that here located in the one level. That means the power for this reactor is not very high and is used for research purposes. Of course, it's not a very correct description of this process, but in many situations you can use it as one of the factors to define the which reactor you see. Uh, Usually, inside of our reactors, located so-called the internal cavity, and these devices looked here elements, and uh, it's used as the support for all our reactor core and the part of internal cavity devices and service to organize the internal flow of the coolant inside our reactors. When we say about reactor vessels, it's the cylindrical structure made by solid forged shell without some longitudinal valves, and the lower part of these vessels, where is reactor core is located, is made in the form of whole cylindrical shell and with some elliptical bottom, without any inside or without any inserts and outsides. The inside and outlet pipes for connections, the main circulations pipelines, as well as other communications are located at least is more high that reactor core. Usually it's a high, it's not less than 1 meters. Of course, it's needed only for uh, purpose of the security and the safety of our research reactors. And usually it's needed for safety for all people and the all construction elements which we use it in our reactors. When we design and some manufacturing for these pressure vessels, the task is to ensure the long term of reliable operations of the reactors. The reactor vessels operate in the very hot conditions. So it's of course very big and powerful neutron fluxes. It's radioactive materials, and it's aggressive and corrosive medium. If we say, for example, about NPP, for these parameters we add the high pressure and high temperature. Why we don't say about the high temperature, high pressure when we say about the research reactors? It's very simple things because, as I say, our reactors, the main purpose of the reactors, it's not produce the electricity, and for this purpose, the high temperature is not needed for us. And of course, we deleted this factor to from the constructions because it's not important. If we build, for example, the NPP, okay, in this case, we must include these parameters and calculate it. But the many vessels for research reactors is needed only to save the reactor core inside our vessels. Usually, when we say about the inspections and repair of the uh, all elements inside uh, our reactor, in our reactor vessels, of course, it's limited, and because they have some radioactive elements. And for working in such conditions, we must choose the very comfortable the materials for us. And usually, for this purpose, as the construction materials for vessels, internal cavity, and the many construction elements, we choose the stainless steel. Of course, when we say about the constructions of fuel elements, for this purpose we use alloy of zirconium and aluminium, but for vessels we use the stainless steels. We can use the two different classification of the stainless steels. For example, we can use it the periodic and austenitic steels, but in the common situation, of course, in the situations of research reactors, we say that we use only periodic steels. When we say about, for example, about NPP, and of course I don't tell you about the NPP because it's the next step of the research actors. For NPP, we use the austenitic stainless steels because they still give us the big properties for and not aggressive. They increase the process of corrosion and have the big strength when we say about the high temperature and high pressure. In Russian, what about dimensions for all these elements around the vessels? Of course, we can build the different reactor vessels, and the main factor which limited us is the thinkings for these reactor vessels. For example, the main constructions of reactors vessels which we built in Russia have the higher in the 12 meters, and in the diameter is the 4.5 meters. Of course, for research reactors, it's not very often requirement, and usually you can see the vessels with the higher, not more than 8 or 9 meters. In the diameter is usually construction is 3 meters. But it's a maximum for all our dimensions, as I say, 12 meters in the higher and 8.5 meters in the diameters. Of course, these dimensions equal only for Russian federations because we prefer and use it for all transport, the reactors and the all elementary elements which have some uh, um, connections with the nuclear energy. We, for this purpose, we use the train. But in the different countries for Europe, for example, we use it the river transport, and of course, in this case, we can increase the all liner dimensions for our reactor vessels. But if we say true, for such reactor, it's not a requirement. it's more requirement which will be effective for MEPhI. But for your understanding, I will be hope it will be enough. Next, constructions which is most important for us is so-called internal cavity, which I show you here. Why? Because it's as I say, they use it for support all elements inside of our reactor. And usually it's some vertical cylindrical part of our reactor with some perforated elliptical bottom in which the superstructure for the fuel elements for the reactor core will be fixed. With the upper flange, the reactor internal cavity is usually installed on the internal groove made in the upper part of the reactor vessels. And you see this part located here. The design of the reactor internal cavity and the reactors provides for some measures to exclude any vibrations and the movement of the reactor internal cavity in the flow of the coolant as well as the of the event emergency situations. From the vertical movement and vibration, the reactor internal cavity is usually held throughout the elastic element by the reactor cover from vibrations in the radial directions, and the shaft usually fixed in the several places along to the high of the reactors. In the upper and the lower parts of the reactor internal cavity is fixed with the dowels mounted by the reactor vessels. And in the middle part, with the tides fixed around the circumstance of the flow separator or some special technological proportions. Here on this figure, you can find these elements located only in the lower part. Here you can see in the low and the right in the left part I show here. You can say these connections which we use it for located our internal cavity and in the this design of this internal cavity we use it to support belt is provided which serves as support for reactor core baffle. These elements you can see on these diagrams on this figure located here, and this belt creates some uh, elements which around and cover our reactor core in which we will be working. Um, this belt or the core buffer is designed to reduce some inversive of the energy releases of some uh, fuel elements which located on the peripheral part of our reactor core, and it also reduces some indel leakage of the coolant of the reactor core, and it's the element of neutron protections for reactor vessels. Structure is the core baffle is the shell which consists of some several faceted rings, and the internal configurations of the reactor core baffle should ensure the spacing of the some peripheral fuel elements in the reactor core, and in its face bell to the fans through holes that provide the highest design to cool the our structural materials. Uploading the core baffle for routine inspections and prepare is carried out conjunctions with the reaction's internal cavity. It means when we want reload our fuel, we must shut down reactors. We must mm, delete all fuel elements from reactor core. Next, we eject the our core baffle, and after this we deleted the our internal cavity and working and prepare it for any different purposes, and watch and with one operate our research reactors. Next, we say about the reactor which located in sour reactor core which located in sour inside our internal cavity, and it's the heart for all research reactors. Of course, today I find the very famous figure. Of course, it's not research reactors. I say it's a very cool figure of first loading of VVR 1000 reactors, and I think it's looked very great constructions. And here you see the fuel assemblies. Usually, when we say about the fuel assemblies, they have for VVR, they have the hexagonal forms, but we must understand the form of fuel assemblies depends from the country in which we produce these fuel assemblies. For example, in Russia is the most famous forms is the hexagonal. When we say about the Europe Union, for these countries, it's more useful the square forms. Sometimes we use the fuel assemblies with these forms of fuel assemblies, with the different and very specific form of fuel elements which located inside these elements. But these constructions have very big difference. We have many different varieties of all forms, of all geometry, which can be used for formed our reactor core. For example, sometimes we use it only some cylindrical fuel pellets to take our fuel elements and fuel assemblies, and in this fuel pellets from which we consist all our fuel elements, we can use different materials. For example, one level of this fuel assemblies will be with the high enrichment uranium. Some part of from these levels will be with the beryllium. And for research reactors, we have the many different forms, dimensions, enrichment fuels, different fuel element, fuel, nuclear fuel, which we use for these purposes. And it's very big stage of any constructions which we use it for design any research reactors. Of course, I must discuss the most famous forms in our country. It's some hexagonal forms which will be used, and usually they consist from reactor core and consist from the not here. They consist from different fuel elements which we located inside our reactor core, and usually it's the so-called the hexagonal forms of this fuel, of course, for different research reactor will be different. And for example, in this figure, you see the fuel assemblies for VVR reactor types, and on the on the left figure, you see the construction of research reactor about which I told you tomorrow or yesterday. It's from VVRC reactor types, and you see that have the at first moment they have the different forms for fuel elements. Here we have the cylindrical forms. Here the hexagonal forms, and the density. In in the MEPhI, usually when we say about the density of dioxide fuels, it can usually consist of 10.5%, 10.5 gram by centimeters per square. But when we say about the research reactors and, for example, we will see reactor types, the density for this fuel is less than one. Why? But we use more high enrichment uranium here, 5%. This not I don't tell you, but I say that this density is not more enrichment, not more than 50%. But for located fuel in this fuel estimates, we use some zirconium matrix inside which located the some granules of our fuel. And of course, the summary density will be less than 1 gram divided by centimeters per square. And these different types, of course, give us the different results when we will say about the working NPP. And of course, we're working with some different informations with these pumps, and we must solve some problems with, and some have some different elements for in, the main construction elements will be different for different research reactors. You can find the form, as I say, enrichment, the high of fuel elements for reactor core, and all these constructions today have some places, and its boundary or only the imagine and the uses for the which produce the uranium-233 and use it as fuel. In not different countries use this technology. And it's the main part and the many words about the construction of research of design of reactor core. And the next, the big subject about which we must discuss is the pumps. Of course, in this part of my lecture, I give you only the general information about any type of pumps, because as a nuclear fuel, as the same the situation is the pumps for different NPP, we use a for different research reactors we use a different pump, and the choice of the pump depends from the coolant or moderator which we use on this NPP. And we start of the term. What is the pumps? And pumps are called the machines for imparting energy to the working environment. And depending on the type of working fluid, it's distinguished is made between pumps for liquid, it's the pump in the narrow sense, and the pump for gases. It's the gas blow and the compressor. And it's the first classification, as we see. We divided by pumps for the gases and the for liquid. Of course, we must say that we have some pumps for solid, but in real life we don't have these pumps. And usually we will be describe the pumps in the most common situations. For us, when we say about research reactors, in many situations is more interested the liquid pumps, because for all and the most economically efficiently uses the water as a moderator for all research reactors. And of course, I will be focused on the pumps for liquids. But about some compressor and the gas blower, I tell you a few words, because we know that have research pumps with the gases. Uh, uh, and according to the principle of operations, pumps are divided into dynamic and volumetric pumps. In dynamic pumps, the fluids move under the forces in the chambers of constant volumes and communicated with the inlet and outlet devices. In volumetric pumps, the movement on fluids is caused by suctions and displacement of fluid due to the cyclical change in the volume of the working cavitations during to the movement of pistons, diagrams, and the plates. Which parameters constructions, and these elements with the green color. Because usually it's more important for us the main characteristics. Of course, efficiency on this, I think you don't have the questions, because if we have the big efficiency for pumps, it's very good. Next, why I detect the volumetric flow and the head? Because for all pumps, it's the diagrams for volumetric flow and heat give us some very specific points of working pumps. And of course, we choose our pumps uh, if we know these points. When our two diagrams will be interact with the same, without themselves. And this diagrams is very important for all calculations. Why I don't say about the rotated frequency? I mean, how many rotate per minute we have in these pumps? Because for research reactors, it's not important. Why? Because for us, is the main role of the pumps, it's the cooling of our reactor core. And because we don't produce a very big amount of heat, it means the cooling it's not so big at the MPP. And this characteristic is not important for us. Next, condition of the medium at inlet, temperature and pressure. And remember you that in research reactors, we don't have the big temperature and the pressure. And of course, if we don't have the big temperature and pressure, it means that these properties of our medium don't change in our reactors. And about which conditions we will be talk about in these situations. Because, for example, usually when we say about research reactors, I will be tell about my favorite VVRC reactor types. The temperature in inlet of the reactor usually consists in the common temperature in the nature, which you see is 20 degrees. The maximum temperature in inlet is 80 degrees of Celsius, of course. And this change of temperature not so big. And of course, it's not requirement very big cooling because, for example, in the pool we have the very big amount of water, and we can overheating any construction materials in on the big temperature. Density of medium is the same as the condition of the medium. And the power. This is very interesting for the moment because the power is very important things. Why? Because in all our research reactors, we create, not we create, pressure will be created in pound. It's the high of the water, which will be like which be located under as reactor core, and of course for change the pressure we must have the uh, peak power, and for the vessel reactors we must give us the circulation of our coolant, and for this purpose the power where have some influence on the working parameters uh, for our working medium. Um, Next classifications about which I tell you, but we will not discuss. Uh, we see what that we have volumetric, blade, jet, electromagnetic, and magnetohydrodynamics pumps. We don't discuss electromagnetic and magnetic hydrodynamic pumps. Why? Because I'm sorry, a few seconds. Uh, uh, we use it for when we say about the working with the liquid metals. And when we say about these working pumps, they have some problems because to give us the circulations of coolant, we must create the electromagnetic waves, and these waves will be have the big influence on all different equipment on research reactors. And we today we cannot say which this influence will be uh, take for our equipment. And because of and of course I don't use it these elements. Blade machines and blade pumps is the most in the main pump which we use in the some nuclear engineering because they have the constant head and flow characteristics. And the jet pumps usually use it only for remove the non-condensing gases in some research reactors at the main circle pumps. They play the role. But for gases, we have we don't use the gases with its natural density. We must increase the density for all our gases because uh, uh, the heat exchange property for all the gases it's very low. And of course, to increase these properties, we must increase the density of our gases. And we start our classifications from the volumetric pumps. And usually volumetric pumps divided by pistons, clutch, rotary, and gear type reactor. And at first, you see the construction of the piston pumps. I hope you know how it's working because it's very famous constructions for pumps. And of course, usually you see, I hope you see, when we say about the engine for any cars, he working on the same principles. And what this principle? Piston pumps have some cylindrics and the pistons that reciprocate. The cylinder is equipped with some valves for suctions and discharge, and with the forward stroke, the pistons and the open valves too, and the process of pumping the working medium into the pressure pipelines take place with the return stroke and the open suction valves filling the volume of the cylindrical, and the precisely of the piston pumps is the frequency of supply and reposition movement. Um, what is the main advantages of these reactors? I'm sorry, of these pumps. It's very easy constructions, but which big disadvantages of this? Look on these diagrams, which show us how change our flow of our medium, which we use for cooling. And we see that in some point we have the maximum, sometimes we have the zero, and of course for cooling our fuel in the reactor core, it's not useful and it's not correct construction because they can give us the instant cooling for our fuel assemblies for our reactor core. And of course, it can create the very dangerous situations in our constructions, in our reactors, for our reactors. Next constructions is rotary pumps. Rotary pumps have some cylindrical rotors concentrically located in our not correct in our vessels. I'm sorry, not housing. No, I don't why I write these terms. And in the radial slots where are the some movement plated which under the working medium of the discharge nozzle. What I can say about this construction? You see this, you in most research reactor you can find these constructions. In most NPP you can find these constructions, but in many characteristics we see this construction. But on research reactor on NPP we don't use it because we have some problems with the efficiency of these pumps, and of course it's very hard to repair in any situations. And in most common situation, we don't use these pumps. Next is the gear pumps. In the gear pumps, as you see, we see and use it two gears which rotate, and of course we usually use these pumps only for working with the higher density of the liquid, because you must understand that, for example, we cannot use it the pumps for the water, and the most famous role of these pumps is give us the circulation of some oil, uh, which we use it for different equipment for our MPP, and we can use it, for example, for pumps, for pump some organic coolant, or the some fuel on the some chemical which pumps is based on the general principles, of course, in the forces interactions of the our impeller blades with the flow of pump liquid which flowing around them. And the first type is the centrifugal pumps, and the main working body of the centrifugal pumps is the impeller, of course, feel rotations on the shaft and carry out the rotor blades smoothly behind in the directions opposite of to the directions of rotations of the impeller. The wheel is instantly installed inside the stationary flow elements of the vessels, inlet and outlet. Inputs and the outlets are combined by the vessels, and the rotor as a shaft with the rotations part mounted of the its rotates in the beginning, and the seals can be installed between the rotations and stationary parts to reduce the some leakage from the pumps and to reduce circulations inside our pumps. Um, when we say about the under the actions of the some centrifugal forces, the liquid is ejected from the impeller, and of course, it's the result of which the vacuum is created in our center of impeller and increase the pressure in its the peripheral parts. To ensure the continuous movement of the liquid throughout the pumps, it's necessary to provide the supply of pumped liquid to the impeller and outlet from it. The liquid enters through the opening in the front disc to the impeller through the suction line, and the movement of the liquid along of the suction line occurs due to the pressure different in the intake basins, atmosphere, or the some central area of the view. Usually in the central part, of course, we have the vacuum and expand as it's expanded the volume is provided in the pump's vessels to drain some part of liquid. Next constructions is the axial pumps. Uh, in the impeller of the axial flow pumps, it consists of the sleeve on which several blades are fixed and which represent some steering curved rings. The pump's impeller rotates as a tubulated chamber filled with the pump liquid when its blade acts to the liquid due to the change of the flow rate, and the pressure in the front of the blade increase and behind it is decrease. And due to the forces generated during this, the bulk of the liquid within of the impeller moves in the some axial directions which determined by the name of the pump, and the front of the wheel its fixed flows rather some elements of supply are instant behind the wheel it depends. Usually, some extra pumps are available with some impeller blades is rigidly fixed on the bashing and with the rotary blades. Compared to the centrifugal pumps, the extra flow pumps have some significant higher flow rate, but it's lower the head of the flow. And of course, usually the efficiency of all auxiliary pumps is reached at the zero point 0.1 and the higher. It means that have the very big efficiency for all these pumps. And next specifications, diagonal pumps. Uh, of course, I read what is the pumps is directly not rapidly as the centrifugal pumps and not parallel to the axis as some axial ones, but obliquely is diagonal for the rectangle composed of radial and axial directions. And in the term of their operations parameters, flow rate, head, the diagonal pumps occur in intermediate position between centrifugal and axial. It's not very famous and not comfortable for me pumps because usually we use it not this types of pump or not we, in most situations we prefer use the centrifugal or axial pumps because for diagonal pumps we have some strange characteristic because in all these parameters they have some medium characteristics, and of course it's not very comfortable for us and use it for any purposes. Jet pump. It's a pump which we usually use for some gases. And in jet pump injector, the flow of the working fluid is accelerated in the nozzle of the working medium, and the enters is a mixing chamber, and which the reduced pressure is established. Chamber is connected to some vessels in which the highest pressure is maintained. Due to the present difference, the medium enters the mixing chamber and the mixing with the working fluid, and further the mixing enters of the outlet and the expanding nozzle in which the static pressure rises and then into the some discharge pumps. What we must say about that some advantages and disadvantages of pumps. Of course, it's consists for all pumps which working with some gases. The main advantages of these pumps, of course, it's very simplified constructions. We don't have the some any moving parts, and we have the higher reliability for any moments in any moments. Many disadvantages. It's the low efficiency. Usually, it's not. It's very less than for some blade pumps, and it's high noise when we use some gases with a high pressure. And of course, it's big problems for all our research efforts. And the last subject about which I tell you about only pumps, not on the end of my lecture, it's too many different constructions of the pump. Of course, I can't find the example of these pumps on for the research reactors, but I must tell you about it. It's two different constructions It's the so-called the sealed pumps and the pumps with a limited control leakage. Between these pumps. And sealed pumps use 310 pumps, which used on the reactor VVR 440. This reactor with limited control leakage, it's a XM 195M, which used in the um, VVR 1000, and which different between two these constructions. In these situations, when we say about the sealed pumps, we limited with the maximum, and we have the not very high efficiency. For example, looked on this red characteristics. The head is 60 meters for the sealed pumps. When we say about control leakage, it's 93 meters. Efficiency in this case 80%, here 52%. Why? And which pumps we more prefer for our research reactors? Of course, we have the less efficiency for sealed pumps, but the main advantages for all sealed pumps is the zero emissions of radioactive materials from these pumps, and it's very important. Uh, in these constructions, we have the very high efficiency, but in any situations, we have the leakage of the some part of radioactive materials. Of course, when we say about the research reactors, efficiency it's not very important for us. For us, is most important the safety for from our reactors. And of course, in these situations, when we say about the research reactors, we used in any situation the sealed pumps because, of course, they have they have not very high efficiency. They don't have the very high head for flow, but uh, the head is not important for our research reactors because we don't have the big temperature. Efficiency it's not important because the efficiency of production's heat it's not important for us, but the safety is the one and the basic principle for working any equipment for research reactors. For because they have the very high efficiency, they have the very high head of flow. And of course, there are our times about this characteristic. I don't tell you. Discussed moment. It's our research reactors. We don't prefer these reactors. This type of pumps because it's more dangerous than tube pumps. Next, the main subject about which and the last subject today is materials about pipelines. Should pipelines. The cost of all pipelines depends from the type of the shoot reactors. But when I say example for tank reactor types, in these situations, we the cost for all pipelines will be equal of the 10% of all equipment which we used on this. Next, pipelines materials. As I say, we can use it the different type of stainless steels. And on these diagrams, you see that these elements. Of course, usually it's three different materials of stainless steels we use it. At first, it's the carbon steels, it's the palladium steels, and the austenitic steels. As I say, and the difference between these three type of materials, of course, it's the so-called the medium which located inside our alloy and which use it. And usually you see that if we have the no very high temperature, we use the carbon steels. If for us is requirement the very strong of our materials, we use the palladium steels. And in the situations of high temperature, we use the austenitic steels. But steels don't use it because it's not requirement, and they have the very high cost for this pipeline. And of course, we can use it because it's not a reason for use these materials. For research reactor pipelines, with the expansions of the main circulation circuit of the reactors, we use the palladium steels, as I say, for pipelines, for reactor vessels, for reactors pipelines, and of course we use it to we can use it the carbon or palladium steels. In for most safety, of course, we use palladium steels because they don't have the very high cost. Usually, they is the cost of palladium steels only in 2 times is higher for that for carbon steels. For example, if we say about the austenitic steels, the cost is 10 times more than for carbon, and of course, it's a very big difference. Of pipelines with the temperature is more than 45 degrees, have the thermal insulations with the surface temperature of 45, 48 Celsius degrees. At the seams, at the welding sites, the thermal installation should allow for its rapid removal and restorations, and dimensions of the pipelines are specific in the millimeters and are usually indicated by the fractions of the products and the numerations. I hope you see these numerations out. The first number is the outer diameters, and after we install the wall of the synthesis. And of course, you can ask me why we choose it 45 degrees and why we use this boundary. Because it's a temperature which show us the time to react on this temperature. For example, if you take your arms and catch the tube, and the temperature will be less than 45 degrees, you don't have the time to understand this moment. Your brain don't tell you more fast, and your arms will be. I'm sorry, I forget the words on the English lesson. Uh, and your arms will be red color, and your skins will be have some damage. But if the temperature will be less than 45 degrees, your brain has enough time to understand that, oh, the tube is very hot, and you can remove your arms from the tube, and you don't have the problems with your head, skins, and the feeling themselves. Uh, Next, back to the end, back to the tube. Uh, of course, is for us is most important not only outside the diameters for our tube, which we use on MEPhI, which we use on our nuclear facility, but is us more interesting the inner diameters. The inner diameters of the pipes is taken dependent of the flow rate and the speed of the medium and requirements, the wall thinkings and the outer designs, outer diameters for the pipelines is based on the strange calculation, of course. For the pipeline, the speed of the medium, uh, it's very important things and depends from the reactors. The higher speed of the chip of pipelines, the total cost for research reactors, but it's have the give us the very big hydraulic losses. and therefore we chose the some velocity and speed of choose the speed for medium in our pipelines. We must calculate the some technological and economical parameters. Or I write these parameters, but I tell you which is most important for us. Usually, when we say about the water, French or some liquid in any situations is always longer. The connection points of pipelines is the sections which with each individual units of on connections and all connections are welded because flange one are used as an exceptions because repair of pipelines is the first in the our circuit it's extremely difficult and of course the welded connections is give us the of connections and we don't have the problem. What I want to create. If you have some questions, you can write and give it to me, and I tried give you the answer on your questions. And now I back to the chat. Give us the generation functions.
Thank you, Professor. Um, yes, we already have one question.
Okay,
It's from
2 seconds.
Julius.
I open the chat because I had some problems with it. Uh, Now I must
I can read it if you prefer.
okay.
Okay, the question
Uh,
is,
which the all right. I see the given the duration of filters in the research actors. All right.
yes.
Describe because the main purpose of all research reactors is the generation of neutrons because the neutrons give us the reactions which we use it for produce radioisotopes, which we use it for um, create some beam of charged particles which we can use it for medicine, which we can use it for medicine, and it's the main role for all reactors. It generates the neutrons. Uh, but many difference, for example, between research reactors and NPP, we don't use it, these neutrons to produce the heat. The heat it's some losses of our okay. It will be enough for you.
So I hope so. Yes, Julius this says thank you.
Not any questions, yes?
Okay, I think we don't have any another one.
Yes, I don't see any questions. All right. If you don't have any questions, thank you for your attention, and see you tomorrow. And tomorrow, I tell you about some uh, silt elements, and I don't remember about which difference thing I tell you. Of course, and I remember I tell you about the heat exchanger which used on NPP because it's very big particle of constructions for all research reactors.
All right. Okay.
All right.
Thank you again, Professor. And so see you tomorrow. And for
Right.
our
See you tomorrow.
also see you tomorrow. Okay. Bye
Bye,
bye.
everyone.
Bye, everyone.
Thank you. See you tomorrow.